Okay, here we go with another biological workout. 3 questions. I'm going to go through my preferred answers and then hopefully you will go away and try and repeat that without help, without support. Okay? And if that's too much of a struggle, you revise your stuff and then you try again. And you keep doing that until you are to the level that you want to be. Okay, so we're going to be testing for carbohydrates this time, just finishing off our carbohydrate series. So this should be episode 3 on carbohydrates. So we're going to be now looking at the final thing, which is how to test for the carbohydrates. So what are the carbohydrates that we can test for? We can test for starch. We can test for reducing sugars. And we can test for non-reducing sugars. Okay, so let's just quickly recap what the tests are. What are the tests for the carbohydrates? What is the test for starch? Well, the test for starch is adding iodine. Okay, and what is the positive result when we add iodine and starch is present? We get a color change from orange, brown to blue, black. Okay, so that's nice and straightforward. We just want the test and we want the result. Okay, we'll get into the steps. That's going to be question 2, is going to be the steps in the method. And step 3, we're going to just go to slightly higher level, thinking about how we can measure how much. Because remember, this is just, is it there or is it not there? That's what we call a qualitative test. We can also modify methods to make them quantitative, i.e. we can measure how much or estimate how much of the stuff is there, how much of the molecule is there, what's its concentration. Right, reducing sugars. We're talking about things here like glucose. Okay, now it's not all monosaccharides, and it's not that just because it's a monosaccharide it's going to be reducing. Some disaccharides are also reducing, things like lactose, maltose. Okay, they are reducing sugars, and we detect the presence of these molecules by doing the Benedict's test for reducing sugar. Okay, we add the Benedict's reagent. We'll discuss the steps in a bit. And if they're present, the color change that we see, it starts off blue, and then if reducing sugar is present, we might see the following changes: going green, then yellow if there's more, then orange if there's more, and then red if there's lots of it. So we can test for non-reducing sugars as well. Now, non-reducing sugars, the reason that they're non-reducing is because the part of them that is reducing is locked up in this glycosidic bond. So what we do is we break that down. So as we repeat the Benedict's test, but first what we do is we break the glycosidic bond. We break the glycosidic bond using acid. Okay, and then once we've broken the glycosidic bond, then we simply do the Benedict's test. Okay, because once we've broken the glycosidic bond, then we should have converted it now to its reducing form. Okay, and again, it's the same color change. In that case, we will get a positive result. So not yellow first, green, yellow, orange, red. Okay, that's our tests. Now we'll just quickly go over the steps in the methods. Starch is easy. We simply add iodine drops and observe color change. Okay, there's no heating involved here. Okay, so all I'll say here is just be clear on your methods. Don't mix things up. If you have a tendency to mix things up, it's because you haven't organized that information properly, so spend some time on that. Right, reducing sugars. What are the steps? Well, one, we do add the Benedict's reagent. Okay, remember that's blue. Okay, but then we have to heat. In order to get that reaction started, the copper ions, in order for them to react with the reducing sugar, we need to activate or supply that reaction with this activation energy. So we need to heat in a water bath. So that this is happening in a tube. You've mixed your reducing sugar and the Benedict's reagent in the tube, and then you place the tube in a water bath at a high temperature. So heat in water bath, yep, 70 to 80 degrees should do it for, shall we just say 10 minutes or 15 minutes? Okay, that should work. And that's it. And then 3, observe color change. Right, non-reducing sugars. How do we do this? Well, the first step that we do is we do the Benedict's reagent. We add Benedict's reagent or do Benedict's test, add Benedict's reagent to heat in the water bath, and see whether it is a reducing sugar in the first place. Okay, so first what you have to do is you do have to confirm that it is a non-reducing sugar in the first instance. Okay, so add Benedict's reagent, heat in the water bath, 70 to 80 degrees C, right, 10 minutes. Okay, 3, result should be negative. The result should be negative if it's a non-reducing sugar. And part of this is not just to confirm, because look, if you took a reducing sugar, you added acid, and then you did the Benedict's test, what would happen? Ask yourself, right? It would be positive, but you didn't really do anything. You didn't confirm that it was a non-reducing sugar in the first place, did you? Okay, and that's what the first part of this method has to do. It should confirm that the sugar initially was non-reducing. So you've got to confirm that adding the Benedict's reagent, heating it, gives you a negative result, okay? i.e. no change of the Benedict's reagent. Okay, once that's done, you go back to your original solution, and then you boil or heat with acid, such as hydrochloric acid. Okay, then you should neutralize, so you can add an alkali solution to that just to neutralize the acid. Neutralize, and then repeat the Benedict's test, and you should get a positive result this time. This time it should be positive. So if you got negative first and then positive, then you did have a non-reducing sugar in the first instance. Okay, and remember that positive result just means our standard color changes going from blue through green, yellow, orange to red. That indicates that the sugar was originally non-reducing, but breaking the glycosidic bond with the hydrochloric acid changed it into its reducing form. Okay, right. Now, our final question is, how can we modify these tests in order for them to be quantitative? Okay, so I've divided it up like this, but the principles of quantitative all depend simply on the color change. So ask yourself, do all of these reactions depend on a color change? Yes, they do. All right, in this case, we go from blue to black, orange brown to blue, from orange brown to blue black. Okay, so we could be measuring either the extent of orangeness, or we could be measuring the absorbance of the blue, okay, blue-black wavelength. In this case, we could be measuring how much of the blue precipitate is still left, how much of the original blue solution is left over once the copper starts getting converted into solid. The aqueous blue copper ions could get converted into copper precipitate. Okay, same here. So we could be measuring color changes. Okay, so in order for any test to be quantitative, we need to know. So first of all, how do we measure color change? We use a colorimeter. Okay, we want to measure how much of this color change has happened, essentially. And we measure that, and we do that using a colorimeter. Now, whenever we use a colorimeter, we do need to make sure that we are measuring absorbance. We are measuring absorbance, but we can't just be measuring absorbance. We need to measure absorbance at a particular wavelength, and that depends on the color the color change that is going on. Okay, so whenever we're using a colorimeter, we need to measure the absorbance, and the absorbance at the right wavelength. At the right wavelength, and that means we got to use the appropriate filter. Okay. Usually, it's a wheel on the side. You just change it, right? Now, depending on the wavelength, now you don't need to know the specific numbers of this. I don't think. I think as long as you make a reference in what you're writing to, I'm going to make sure that the filter is right for the color change that I'm detecting. Okay. So if you're measuring blue, the opposite color on the spectrum, that should be your filter. Okay. If you're measuring green, for example, then it should be the opposite color of green. That should be the filter that you use. And if you do that, then you're going to be measuring the intensity of the right color. Okay, so we set up the colorimeter like that. Once we've done that, we also need to calibrate the colorimeter. And we must do that with something that has zero amount of that color. Okay, so once you've set your filter, you've got to put something that has nothing of that color at all. And we usually do that with water. Okay, so we zero the colorimeter with a water control. And then we're ready to use the colorimeter. But before we do that, there's another aspect that we need to make sure that we do, which is we need to have known concentrations. We need to know that a 5% solution of starch has an absorbance of so-and-so, and that a 1% solution of starch has an absorbance of so-and-so. Okay? So we need to have known concentrations of starch to begin with. So known concentrations of substance or molecule. Okay? And how do we do that? Yes, you guessed it. Everyone's favorite. Serial dilutions. Okay? So I'm just going to very quickly go over the concept of serial dilutions. You have one tube or bottle of your substance where you know its concentration is whatever, 10%, for example, and then you simply do like 50% dilutions or 1 in 10 dilutions with water. So you've got some other tubes, right, with a bit of water in them, known volume. Then you transfer some of this into here, you mix it, you transfer some of that into there, you mix it, you transfer some of that into there, and so on. And in doing so, you go from 10% to 1%, to 0.1%, to 0.01%, and so on. And then you've made a range of concentrations. Once you've got your range of concentrations, you measure the absorbance of your known concentrations, and you get a calibration curve where doesn't meet there, where you've got the percentage, your known percentage concentration, so the absorbance. So you've got your absorbances on the y-axis, and on the x-axis you've got your concentration. Okay, so for each concentration of solution, you're going to put it in the colorimeter, measure the absorbance, plot it on the graph. Okay, and then you're going to fit a curve to that, and then you take your solution that you don't know the concentration of, your unknown. Okay, then you measure you do the test. Okay, you do the test, and then your resulting solution, you want to measure the extent of the color change. So you put it in the colorimeter, you measure the absorbance, and whatever absorbance comes out, we read it off the graph. Wherever it hits the curve, we go downwards towards the x-axis, and then we figure out what its concentration must be in comparison to our known concentrations. one thing I forgot to mention. Right, when the color change, so in this part, okay, when we're talking about the Benedict's reagent, when the color change happens, the color change is due, the color change that we know about, or that we've discussed, is happening due to the presence of a precipitate. You should not be, but you don't want to measure that directly with a colorimeter, okay, because the precipitate is a solid, so the thing that's causing that yellow color or a red color is a solid. Now, solids should not be, solid precipitate should not be measured with a colorimeter. So what we're going to do is we are going to filter. So once we've done the Benedict's reagent, we need to filter away the precipitate. And what that's going to leave us, with is a series of tubes which are a varying range of blue. Because the more copper ions that have been converted to copper precipitate, the less blue that solution gets. So 1% solution will have lots of, that will have a lot of reducing sugar, so there will be a lot of copper that's been converted to copper precipitate. So when we remove the precipitate using a filter paper, okay, there's not going to be a lot of color of blue in that tube. Whereas one of my lower solutions, right, because that didn't have a lot of glucose, there would be less of that reaction that would have happened. A lot of the copper in here would still be, therefore, in solution, not converted to precipitate, and therefore this would be very dark as a result of the Benedict's reagent. Okay, so I hope you're getting the idea that what we're measuring now is not how much precipitate has been converted into, how much copper has been converted into precipitate, is how much copper we have left over. So we've got a series of blue solutions, not a series of red solutions, okay? That is very important, that you get your head around that. If you're not sure about that, please discuss that with someone. I would recommend that, that's just a quick conversation that you need to have, okay? But I just thought it's very important to mention. So the qualitative test is dependent on the color of the precipitate. The quantitative test is dependent on how much copper aqueous, how much copper ions you have. So this is all about measuring the amount of copper precipitate, yeah, or how much precipitate you can see being formed, and this is about how much copper ions in the Benedict's reagent is left over once some of that has been converted into the precipitate. At this point, I am done. This is kind of how I would recommend that you do it. The most valuable part of this is these questions. Please take those questions away. Practice doing something like this for yourself. I don't know why this couldn't fit on an A4 sheet of paper. You can probably fit a little bit more information if you do it like that yourself. Okay, 3 questions, practice answering the questions. Don't constantly rely on the information going in to your mind. The quality of your revision is how much you can produce from your mind, not how much information you can put in your mind. Okay, so this is where we finish. This is where you get to work. Good luck.